Watching. Okay, so for the shortest paths, the thing is that we would like to be able to find the shortest path between two routes, and we're going to be using some kind of metric that is going to allow us to find what is the shortest path. Basically, because every edge is going to be having a weight, and we would like to minimize the weight from point A to another point B, let's say. Now this is some kind of very known problem that has its own specific challenges, especially if we have negative weights. But I'd like to talk about the fact that if we have a negative weight, it's going to be really, really challenging, especially if we have cycles within those graphs. Now remember what a cycle is. A cycle is a repetition of a set of nodes. So for example, let's say if we have something like this and we would like to go from B to F, what is the shortest distance? Based on the weights. If we say that this is the weight, which is the distance will take us B, C, E, F, because this is 10. But if I go B, A, C, it's going to be 4 instead of 5. From B to C directly cost 5, but through A cost 4. So I can have B, A, C, E, F, or D, F. B, A, C, D, F. From the C, if we go from C to F, that's 7, and that's 5 here. So actually this one is shorter. So when we have non-negative weights, that's fine, that's easy. We just need to pay attention to try to find which one is the lowest cost, the path that is going to cost us less. But there's a problem. Imagine, for example, we have something like this, -8. Now -8 means if you have from, let's say, something that takes you from D to F, wherever. So you go here, D, A, C. D, A, C is going to be much less than, and if you repeat 2 times, it's going to be much less than if you repeat just once. So this is going to be something, anyways, that is kind of weird. But why would it be negative? Well, there's maybe some situations where it might be interesting, but we're not going to be talking about those cases. Now, the case that we're going to be talking about is that we're going to be talking about these situations like these, when we have non-negative weights, and there's an algorithm by these guys, Dijkstra, who I think is Polish. I'm sorry? Dijkstra? That's how we pronounce it? I don't know. Dijkstra? Okay. Is he? Anyways, he's from Poland, I think, if I remember. Anyways, he found an algorithm that solves that, and it's some kind of like very known. It becomes like some kind of reference in how to solve this shortest path problem. Now, before going into the details of those, I just would like to show you how these works. But I don't want to show you with this table because it might look a bit complicated, but I'd like to show you also on a simpler one that I'd like to draw myself. Now, not like this, not like that, but just go in here. How can I increase maybe the size? Yes. No. No. Which one might be nice? No. Maybe this one? No. I'm not. Let's just stick to the one that we know. Can I? The size. Where's the size? Here. Okay. All right. That's better. All right. What I would like to do is to see we have this graph, and we'd like to go from B to F again, right? So how does this work this algorithm? Well, basically it just tries to keep track of the following thing from where we start. And actually I've included a video that I can show you later on, but well, I'll just put it there. You can have a look at it because it uses this simplified table that I'm referring to. So what I'm going to refer to this is having a table that has 3 parts: all the vertices, all the weights, and the predecessors. I'm going to remember what if I'm in a vertex, from where did I come to reach that vertex? That's the predecessor. So that's what this means. So this is the vertex. So the list of all vertices that we have, what are the lists of all vertices that we have? A, B, C, D, E, F, right? That's what we have. So I'm just going to use this A, B, C, D, and then erase something. And continue with E and F. So that's what I would like to represent. Now, among all these, now the algorithm works this way. It keeps a list of all these vertices, and it keeps a list of those that are visited. I'm just going to put them like in some kind of a list here. Unvisited. Unvisited vertices. This doesn't need to be anything. You just need to put all these elements here. So I have not visited any of those, so I'm just going to put them all. So I remember all those that were visited and those that were not visited. So I have not visited none. I have not visited any, and all of these needs to be visited now to check them. Now, how do we start? Is that we're starting from vertex B, so we can just follow the same result. So when we start from a vertex, we're going to put the weight of that vertex to be 0. That's the initial weight. And everything else is going to be infinite. So that's how we start. We just say this one is 0. That's where we start, where we're starting from. And all the others are going to be infinite, just to be the biggest number possible. Because what we'd like to do is we're going to be checking the weight from each one of those. And every time we find that this is going to cost us less, then we're going to follow that path and memorize the cost that took us up to there. Now, what I'm going to do too is maybe represent this graph, not like that. I'm going just to put this B, and then we have B that goes to A. This is a directed graph, so I'm going to put these arrows, and this is A, and the cost is 3. And from B to C, so we have C, we have D, E, and F. So we have this, and A to C, D to A, and C to D, C to E, and D to F, and E to F. And we have 5, 1, 2, 5, 5, 1, 2, 5. Just make sure that I'm not doing any mistake. 4, 5, 1, 4, 5, and 1. Okay. Now that's how we start. So we start from here. So this is our starting point. What we do is that all of them, what we said, we put each one of these, that initial weight to be in that, to have ourselves be in that vertex, is what we took note of it. So we started from 0. And everything else is going to be infinite. What we're going to be doing, we're going to be looking how much it will take us to reach here, every vertex. And then we calculate that. And if we find that weight is going to be less than what we initially have, we're just going to remember and put that weight into that table. So let's say we start from B. Now what are the options that we're going to be visiting? Well, first of all, we're going to say that we've visited the B, so we don't need to visit B. So B is going to be now in this list. Then what we do is from B to A it will cost us 3. And from B to C it will cost us 5. And which means now what we need to do is that we need to update now the A and the C, because 3 is less than this infinite. So we are going to do this update, and I'm going to remove this and remove the for the A and for the C. And what I'm going to do, A now is 3 and C is 5, and I need to remember from where did I come to reach that weight. So the predecessor of A was B, and the predecessor of C is B. The others, there's nothing. Is that okay so far? So now that's how this works. From every node, I'm just going to check where can I go and see the weights, resultant weights. Basically what happened is 3, basically I just use this because I'm starting from 0. I'm always adding 0 plus this and see how much it costs me to reach that node. And that's what I'm going to do, for example, now by going to the next node. But which node now I'm going to check? I have now 2 next nodes from B, A and C. We're always going to check the lowest one. So now the next thing we're going to check is from A. Now from A, where can we go? Only C. So from A to C, how much will it cost us? It took us 3 to be in A, plus 1, that means it's 4. Now it was 5 before, but now we found the shortest path, which is 4. We're going to remove this 5 because we found the shorter one, and then we're going to put the 4 here. By putting the 4 here, we need now to remember that this is not 5, but it's 4. Yes, and the position was not coming from B, but coming from A. So now I'm just going to put this to be 4, and now it's going to be A. Or that's a word A. Come salam. And now I have visited A. I need to remove it from this unvisited and put it in the list of those that are visited. Now among the others that are remaining to be visited, there's only one, there's C. So I'm just going to go from C and see where should I go from C there. From C I can go to D and E. If I go from C to D, how much it will cost? 2. Then what's the total cost to reach D? 4 plus 2, 6. And what's the total cost to reach E? 8. So that's what I'm going to do, because these 6 and 8 are smaller than these infinite here. So I'm just going to remove these. So D and E. And I'm going to put the values. For D it's 6. And I need to remember that I came from C. And E 6. I need to remember that I came also from C. And it's not 6, sorry, it's 8. Let's delete that. And that's 8. And the predecessor is C. Now we've done all the calculation from C. We remove it and say, okay, we're done with the C. Now among the 2 ones that are remaining to be visited, which one has the smallest weight? 6 is D. So because of the 6, so we're going to look now for D. Now we're going to have a look at D. What is going to happen to D is from D, where can we go to reach the F? Well, there's only one thing that I can go, is F with a cost of 11. 6 plus 5, that's 11, right? So I'm going to put that in here, so remove this, and then 11, and I remember that I reached that from D, and there's nowhere else that I can go, so D now is done. Among those that are remaining, only E, so from E to F will cost me 9. So 9 is more than this 11, which means I'm going to remove this 11 and keep this 9 now. And I need to update this here. So now it's not 11, but it is 9. And it's not coming from D. So I just said 9 and then E. And now the E is visited. So what is remaining is F. F is what we want to be. So we're done. Yes?
And why you go from C to D while it's shorter from C to E directly? It must be
Well, when I go from C to D, while it's from C to E is shorter.
yeah,
How do you know it's shorter?
to reach F.
How do you know it's shorter?
I can calculate this.
Because you can calculate.
Yeah.
But for the computer, the algorithm doesn't.
So,
So we need to have some kind of general rule that will always work. We check all the different possibilities.
so that's why.
That's why, yeah. So, but what's the rule is we just always check with the minimum smaller one and see if we can still reach. But if we can't, we just check the others. So we always check all the possibilities like that. Yes. So now that I have reached here, how can I know the path from here? So you see, I want to be in F. So before F, the predecessor of F is E, and the predecessor of E is C, and C is A, and A, the predecessor is B, and this is from where we start and from where we go. And this is the shortest path that we have, B, A, C, E, F. And that's how we can find it. Is that okay? So see, this representation is like this. But it just keeps all together in one place. So we started from, let me just again do it. So we started from B. So we put, initially we start from 0 and everything is infinite. And basically why I would like you to do this, to have understand this, because this is showing us the steps. And in the final, we're going to ask you a question about this. And I would like to see the steps. So if you make a small mistake, it's not the whole thing is going to be false or wrong. So I'd like to find something. Yes?
Same has to be the same like rule like this one, or
Same like this one.
it can't be like the other one.
This one, because this one we can see the steps that you do. So if you make any mistake, we're going to have, we don't know what. If you do that, the other one, and make a mistake, then I cannot know where you did the mistake. I'm going to give you 0, for example. Or but for this one, I can see if you're close or something. So that's why I want you to try to understand this. But let's have a look. It's exactly the same, except now you just need to hide some parts of it to see only one part. So we start from B. Now we just put everything to be the infinite, and then we see what way can we go. We can go from B to A and B to C. So that's why we're going to be putting this 3 with the predecessor to be B, and C to be 5 with the predecessor
Because the shortest path.
to, I mean, this is the predecessor.
It's not B.
This B is the predecessor from A. This is the final one, but I think this is where it's coming from. Yes.
When you go to C, you should the predecessor A because it's coming. It's the shortest one. So
Oh yes, you're right. So
to
yeah.
A to C. That's here.
So, but initially we went from C to A through B, but then we realized there's another shorter one.
Yeah.
We go through A. So that's why I said this is like the predecessor, But the final one is this one that we're going to be seeing. This is like some kind of temporary one, because here, see, the first time my predecessor was B, because I came from A to B and from C to from B. But then later on I will find the better one and then I will put it there. But here, for example, this initially this is what I found. And then what happened is that I found that from A, from these two, now I need to go from A. Now from A, where can I go? I can go to C and only C. So that means for C, I'm going to, in the predecessor, because of A, I'm going to put this calculation now, because it's smaller than what we are looking for. Now from C, where can we go? D and E. So the D, we're going to make it 6, and the E 8, and because we're coming from the C. And then we're just going to start with this one from the D and see what is going to happen. From the D, where can we go? We can go to the F, and how much it cost us? 11. So this F now is 11 coming from D.
From E is 9.
And from E, it costs us 8 to go from C. But now from E to F, it costs us 9. So on the F, the cost is 9, and then it's coming from E. So that's I don't know if I feel like I have more made you confused than explained it.
This one's confusing.
It's confusing. Let's get to it.
Yeah, but so if, anyways, so this type of thing is not as easy. If you want to use it this way, just make sure that you show me the steps then. I don't mind. Well, what are the? This one is easier, yeah, of course.
Like show the graph, you mean?
No, for example, you see, if when I deleted, let me just.
Ah, you mean when you did it like the.
Yeah, when you deleted, well, I don't know. Sorry.
When you did it like a D.
So each one of them, you see, let's see. I just would like to maybe do it in a better way. Let me try to show it to you this way. Let's say. Now, if you want, you can just do it this way, and that will be fine with me. Let's say we set all the vertices. No, the vertices. I'm going to show them. They're not changing anyways. So the vertices are okay. They're not changing. We have vertices that are A, B, C, D, E, and F. Now for this one, this is the one with the weight and the predecessor, right?
Yes.
So let's do it in a way when I'm going to show you the steps. Now we start from B. I don't need to put this. I'm putting this here just to make them clear, but we'll have the information here anyways. So I'm starting from B.
Which is 0.
Okay, let me stop. I'm just going to put the 0 here, the infinite. So I'll just leave some space so I can just strike it and put something next to it. So now I start from B. So from B to A, it's 3, and so I'm from B to C, it's 4. So A now is not infinite, but it's 3. And coming from B. And C now is not infinite, it should be 4. And coming from B. Then I'm going to check which one. So B now is done. So I'm not going to go back to it anymore. Yes.
I think it should be A. If it is 4, it should be.
I'm sorry.
If it's 5, it should be.
Yeah, it should be 5. I said it should be 5. We start with 5. I was misled by this number here. It's because we started to be 5 here. Let me just stop. I'm looking for this. So, because from B it's going to be 5, not 4. and this 3. Okay, so it's 5 and the predecessor is B, and 3 predecessor is B. We're done with B, right? Now next step, the smallest of the two that I can go from. So the A. Or from the A, where should I go? Where can I go?
Always
To C. So from A to C, it will cost me.
one itself. So 4.
That means the total is
4.
4. And now the predecessor is not going to be B,
A.
but A. And then
We have the D and E,
where can I go?
You have a D and E.
No,
which is 6 and 7.
I
You can go to D.
I had before the 2. Now I finished with the A.
Now we have the C.
Now we will have the C.
I'm going to have it the C now. Yes. So I'm checking the C. So from the C, what can I go? D or E. So if it go to D, it will cost me 7.
6. It is 4 and 2.
Sorry, I forgot to update to 4. So it's going to be 6. So I'm confusing you more than I'm helping you. And you're explaining it to me. The other table is easier? Good for you. I use whatever you find easier. I'm just trying to explain what if I would like to use this one, I'd like you to follow the steps.
What we took in the computer communication much easier than this.
Then this one. In computer communication, you have this shortest path, the least cost. Yeah,
The same diagram here.
like this one or the other one.
No, the other one.
Like this one.
Yes, the same diagram and the table is different.
Which table is? This is a table. You
This
said
table, I mean the diagram for A, B, C, D, it's the same.
which part? These ones as well.
No, I mean the diagram in the left, on the notes.
This one,
The graph,
the graph.
is it the same? But the table, we put the sets of node
Okay.
and each node and their path. Its path
And the path.
for
Okay. From each node, what's the path that goes from it?
what is each path.
Okay. So, for example, now we've seen this. Now the steps, right? I can see the steps that I'm doing here. For example, from C to D is going to be now 6, and the predecessor is going to be C, and E is going to be 8, and predecessor is C. I'm going from there, and then from these two, from D, I'm just going to go to F, which cost me 11. So from D to F, now it's going to cost me 11 coming from D, and then I realize that from E to F is going to cost 8 plus 1, that's 9. So I'm just going to strike this, make it 9, and then this time I'm coming from E, and this is where I'm going to stop. So that's what I mean with those steps. Now everybody, and if you would like to represent this way, that's fine. Just show me the steps. Now let's see this representation that Ali is talking about. Now I'm curious, I just would like to know about it. So you said that you put all the vertices, and then you said the path.
Yes.
So the first one is all the vertices, and then the path, and what else?
Each vertices with their path.
Okay, so I'm having A, B, C, D, E, and F. Okay, now we're starting from B, so what should how would you fill it?
We start from B.
From B, yes.
We want to go to A.
To A, yes.
The path for A is B to A.
So on A, on this line A, I'm going to
Yes.
put B
To A.
to A like this.
Yes.
Okay,
And
but I'm going from okay. So you just represented the predecessor where I come from B. But what about the weight?
the weight is we put the weight.
Where?
We have to write.
You have to write it. Well, come on. Well, you'll show us one day, because then I don't know if it's going to be easier for you to do it on this mouse. But anyways, if it's easy for you to do that, fine. I just want to have like a method that does. I mean, the algorithm is what's important. How we represent it, it's another story. But Now, what's important is how these things work. Yeah.
Yeah, but the table in the slides
Yes.
will come in the final.
Well, it doesn't have to be filled like this. It
Yeah,
can.
So if I took your way,
Fine.
It should be correct.
Yeah. Yeah. So if you present it the other way, like this one that I was explaining, by doing this one, that's fine for me. Yeah. As long as I can see the steps. You see, it starts from here, and then I remove it, so I can see now the steps, basically. So that's what's important. The rest is how we present those. So that's not that a problem. Yes.
Maybe like a comment on the right to make sure that you know.
What kind of comment?
Like I'm going now from A from B to A because it costs 3.
Well, obviously, it's here. I'm not going to have to look at there unless this is not clear. But if you just follow these steps, showing me that this was like infinite, and then it was like that, then it was like.
Just to make sure if I missed something here.
Well, I'm not sure. Well, I'm not going to honestly read a lot of text. If I'm going to mark, I want to mark quickly. So I don't want to read things that are already like a duplication of something that is going to be summarized there. I will go for the summary. But if something is not clear, maybe I might go. But yeah, you can try. It doesn't hurt if you have time to do that. Yeah. But my main idea is that I would like you to understand the steps that are done. And that's the most important part. The rest, how we represent these, this way or not, that's another story. So, but at the end, this is the kind of thing that was done. We go from 0 to 3, then to C, and then, this one was just an option, but at the end, this is the path that we would like to reach the F with this weight of 9. That's maybe another example. And you know what? I just would like to discard, just so we can practice this. I just would like to take this, create a new slide, and paste it. Increase it. Let's just practice. Okay, tell me what is the shortest path, knowing that we start, let's say, from D.
D to what?
D to
The last point.
To C.
The last
Yeah, to C. Let's start from D to C. I think it's a different solution that we have there, but it doesn't matter. Let's just have something that we can practice. So let me just show you this like this, so it'll be easier. And let's say we would like to start from D, and then we would like to reach C, is our final state.
D, A, E,
Yes.
F, C.
Now, well, I don't want you just to tell me yourself how this works. I want you to tell me how the algorithm is going to find the shortest path. That's what I'm interested in.
We want to do the table or?
Well, we can just do the table, but what I'm going to do, actually, let's do the table. That will be easier. Let me just push this up so we can draw some things down there. Now we're starting from here, and I would like to reach the C. So the table is going to have all the vertices, the weights, and the predecessors. I'm just leaving some space to have a lot of place to write. So we have, we have A, B, that's a kind of long thing to type,
Yeah.
B, C, D, E, F, I don't have space for those, E, F, G, H,
I, J.
I, and J. Well, all the best for me too. Okay, now you know what? That's not. Let's do it professionally by
Let's
resizing this a bit,
make it smaller.
and so we can have some more space. All right, now probably we have enough space so we can play around. And this is I'm going to use even this top part. So these are the vertices, and the weights. So V for vertices, W for the weights, P for the predecessor. And we have A, B, C, D, E, F, G, H, I, and J. Now the initial weights are going to be infinite for all except
For D,
except for D, which is going to be 0. So you know what, I'm just going to put this infinite instead of being lazy. So infinite, infinite. And by the way, how can you program infinite? In programming, how can you make it infinite?
Make it no.
Well, there's something I'd like to show you. That's what I wanted to know if you know about that. But it's good that I asked. But how can you put in infinite? Well, depending on what's the data type of the weight. Now, let's say the weight is an int or a double. You can do something quite interesting, which is you can Google. This is the first thing you might do. For example, if you don't know that, you can Google. Okay, what is the maximum value that I can put in an int? That would be the max value in int or in Java. So this is going to give you some kind of a number. Okay, the maximum value will be this number, right? But what you can do as well is that instead of you typing this number, you can get it, because integer dot is going to give you the max value, which is that number that you were looking for. So instead of you typing it, you just use this to be the max value. That's how you can put the maximum number that can be held and stored inside of a data type. You guessed it probably. Double has it. Max value, which is all the best trying to understand this. How many zeros is there?
You have a max value, so it's a zero, it's give me an error.
I'm sorry?
If it exceed the max value,
Yes.
give me an error, but
Well, you know, it depends. Actually, it will give you some kind of a mistake, but it's going to do it, the operation, especially depending on what you're trying to do. Now, if you're trying to put more than what you want, it is going to try to, and there's going to be something. I mean, it's going to do that, but it's going to be an overflow. But it's another discussion. Because it's a negative and positive, and this is because of how it is represented. You remember, how do we represent a negative value in just a set of zeros and ones? So there's a 1 bit that is going to be the bit for the sign, right? 1 bit is going to be reserved just for the sign. 0 means positive, for example, or 1 means negative. So if you fill these, you increase the number, the zeros and ones are becoming just filling, and then because now we have, let's say on 16 bits, 15 bits for the data, 1 bit for the sign. But if you keep increasing, you're going to use that bit as well for the data, which will make it negative. But I don't want to be negative. That's why you can try that if you put a for loop or while loop, a while loop that doesn't stop, but it keeps increasing. So you start by 0 plus 1 plus 1 plus 1 for an int. At one point, you put your question while the number is positive, increment. At one point, it will stop. Logically, it shouldn't, because if you have a loop, okay, let's do that.
because in calculator, doctor, you know, sometimes when you put too much number, it's
Let me do this. This is not data structures anymore. This is Java 1. But let me show you this. Let's say I have int count is equal to 0. Now this is a while loop. No. That the count, as long as the count is positive, increment. Now this seems to be some kind of infinite loop, right? I'm just going to make it 1, right? So it will be true the first time. So it's an infinite loop, but it's not. And I can display the count after. I can display it inside, but I just would like to display it inside so you can see the count changing. But just print, not print lines, so we don't have.
Give it screen.
Yeah, let's go and see this. Here you go. It's increasing. It will take time, but actually, you know what? It's taking time because it's displaying information. If I'm not displaying, what I mean with displaying, look at what is going to happen. If I just remove this from inside the loop and take it outside and put a printer, oh, it doesn't matter. Let me run this. Poof! Immediately you got the something. Why? How comes? Adding positive numbers gives you negative numbers. How is that possible? How is that possible? Because the weight is represented again. Now, these are. No, it's just built into to work the way it's working. Now, I don't know if this is going to show me a word or I don't know. Let's see if I have. Yeah, this is a binary. Let's say this number. You see, the more the number increases, the more bits I'm using to represent that number, right? Now, what is going to happen is that let's see the last big number is this one minus one, this two. So let's me type that. So let's have a look. 2 1 4 7 4 8 3 6 4 7. You see that?
This is still positive.
It's the maximum positive number that you can have in an int. An int has how many bits? 8, 16, 32, 16, 24, 32. So in the 32 bits, that's the maximum int that you can have. If you add 1,
It's gonna be
0, 0, 0, 0, 0, 0, and then 1, which is this number here.
The last one make it negative.
Because this last bit here is just used for the negative sign. So if you use it now, if I add 1 to it, if I do plus 1, what is going to happen is 0, 0, 0 plus, and this is the 1. And this is this number minus this number here. So that's why when you increment, it just goes beyond what was planned for, and it's going to use the last bit that was used normally for the sign, but use it now for the calculation. And that's why this adding all positive numbers becomes negative, just because of the way it is stored inside. So, but that's, I don't know how we ended up here, but I think we were talking about the maximum number of an int. And anyways, and why is it the maximum blah 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 and etc. So we don't care about these things now.
back
Just
to the real life now.
I'm sorry?
Back to the real life.
That should what?
Back to the real life.
Back to the real life. Yeah, well, back to the headache, I would have said. Let's now go back to this. So we were saying, how can we represent a max in this infinite? Well, that's how we can do that. Based on the data type of the weight, you can use this max value, which is going to give you the maximum value that you can put inside that data type. Now, okay, from here, so the algorithm, what it will do, it will start from D and see what are the different places that I can go from D to. So I can go to A, which means it will cost me 4. I can go to H, it will cost me 1. And now I'm done with the D. Now which one I'm going to check now? Which path? I have two ways now, A or H. H is the smallest weight, so I'm going to go for the smallest. And I'm going to see where I can go from H to. So H I can go to E, which will cost, I forgot something, yes. The predecessor. The D. And for the H, the D. Now from the H, I can go to E and I, and that's it. So from H to E, it will cost, because it's smaller, so I'm going to put the cost, it will cost, no, 6. It costs already 1 to reach H, so plus the 5, it will be 6. So from E now, it's 6. And I need to remember that I'm coming from, I came from H. And then for this, which one? The I will cost now? Now let me write the cost here. So I said 0, 4, we said 1 here. Now from 1 to, from H to E, it will cost me 6. And from H to I, it will cost me 9 plus 1, that's 10. So from I now it's 10. And the predecessor is H. Yes.
I doesn't have any weight for C.
I'm sorry? I doesn't have. Well, it doesn't matter. I mean, that's how the algorithm is going to
Okay, that
try to find. Now it tries to reach the C, right? But it won't. So we will just keep going. Now, what is the next step? I finished with what? Which one? With H. So I'm not going to see H anymore. So I'm done with it.
Include the A.
What about the A?
Include the A. No.
Yeah. Now I have A4, and this one 6, and this one 10. So this means among all these, I'm going to check the A, as you said, and from A, where can I go? To E and to H. So to E it will cost me 5. 5 is less than the 6 in the E, which means I'm going to change this and put it 5 because I found the shortest path from E. Instead of this being 6, it's going to be 5, and the predecessor is not H now, is A. And then from A I can go to H. It costs 14. I'm not going to update that. I'm going to leave it because 1 is cost less. So I'm not going to update this by going to.
have one way.
So I'm just going to give the best way to go to H is through D. It will cost me 1. I'm not going to change that. Okay?
And we visit A.
Now A is done.
No 5.
Now we check what are the remaining. E and I. The smallest one is the E, so we check with the E now. From E, where can we go?
F.
Only to F.
A.
So E to F, it will cost me 8. I'm just remember this is coming from E. And I'm just going to write 8 here, and E is done. Now what are the remaining ones? I have F and I.
I.
The smallest
A.
is F. So I'm just going to check from F. From F, where can I go?
And
B, C, and I.
and I.
So if I go from F to B, it will cost me
9.
8 plus 1, that's 9.
And A.
So B, it's going to be 9 coming from F.
And also
And then C, or I, let's say I because it's the same, right? I is, oh okay, I found the smaller one. I is going to cost me
9.
9 coming from F.
And you have a G.
And then I'm just going to change this. Now it's 9. And then I have the C, which is going to cost 11, because from F to C, it will cost 11. So C, now 11, all coming from F.
We don't need G also.
I'm sorry?
The G.
The G? Yes, we do need the G, because F goes to G as well. 8 plus 7
15.
that we put in G. So G now 15
From F.
from F.
Now we finish it.
And we're done with F. F goes to a lot of, it goes to B,
C, G.
and we updated it to the C, and we updated it to the G, we updated it with 15, and we have the predecessor. Just make sure that we do not forget anything. And then the I, and we updated it. So now F done. So among the ones that have not been checked, which one is the smallest?
B and I.
Now we have both of these, B and I. While we have to choose one of them.
B.
We go from B,
Difference because
we go from B.
B, C.
So from B, where we're going to go?
C.
B to C with the cost of 11. Nothing has to change. So it's not less than.
Oh, no need to change.
So it's not really needed. So don't need to change.
Now we go to
Basically from F to C is, if you go directly, it costs 3. If I go through B, it costs 3. So it doesn't matter. So
But you need to pick
the shortest, well,
F to C.
Both are the same.
but we already found it, so we're not going to change that. I mean, according to the algorithm, we only change when we find a shorter one, less than in the weight. So we haven't seen less than, so we just keep going. So that's why I'm not going to change this. That's mean the predecessor of C, as you can see, is still F. We have not changed it. So B now is done. Not going to check it again. Now what is remaining is the other I. The smallest one is the I. Okay, from I, where can I go? To J. So from I to J, it will cost me 11. So I'm just going to write that 11, and remember that I'm coming from I. Any other place? No. So done with I.
You are done with the C, right?
No,
Why?
because I've not reached C. That I'm going to check if from where I can go from C. So now
J.
I have what is remaining. Those that are remaining, I have C
G,
and G
and J.
and J, and we have C and J that are both 11. So I'm going to start with one of them.
J.
Let's say whatever. Okay, this is J. So from J, I need to go from. I can go from J to G, which will cost me then
One. Both.
1. So it will become 12 instead of 15. So I found the shortest. So I'm going to now remember it. So J now instead of 15. I found the better one with 12, coming not from F, but from J.
And we are done with J.
And done with J.
And C.
Now what is remaining? C. And from C, there's nowhere to go, and this is what I want to be. So done with C. And then
Same.
with the J, nothing where to go, done with J. And that's how I can find my path, the shortest path to whatever I want to be. So I'm going to go to C. So before C, it's F,
E,
and then before F, I got lost. E.
and for E.
Before E, it's A, and before A,
A,
it's D,
D.
And D doesn't have it.
and before D
Nothing.
is where we start. So we end up going from D, A, E, F, C, with a total cost of 11. Yes.
So this table can show us the path for anything, but we have to start from D.
Yes, 18 starting from D. So now if you'd like to say, okay, what's the shortest path from D to J, sorry. So I just need to go from J, and then I find the shortest path. So go J, then I go from I, and then from I come back
F,
to F, and then from F to
E.
E, basically the same thing, same thing.
We will take the assignment too.
I forgot completely about the assignment 2. You're right, we have to. Yeah, let's take that. So I hope it was,